Okay, we're ready to get going here. I'd like to thank Governor Nixon for his support of the university system, certainly public higher education, and for being part of the Energy Summit today. We certainly applaud your leadership in cultivating greater collaboration and investment in energy solutions and the creations of new jobs for the state. Our next speaker is Dr. Richard Sayre, the director of the Enterprise Rent-A-Car Institute for Renewable Fuels at the Danforth Plant Science Center. Dr. Sayre is one of the nation's leading biofuels researchers. He's working on using algae as a power source for cars, trucks, and aircrafts. This research could have significant impact on our energy production, given the rising cost of oil, and has the benefit of not competing with the nation's food supply, as does corn-based ethanol. In keeping with the Danforth Center's global vision, which is to improve the human condition through plant science, Dr. Sayre is also involved in improving the nutritional value of cassava, a food staple in Africa and other parts of the developing world. He served as the director of the Bio Cassava Plus program at the Danforth Center, a multinational development program funded by the Bill and Melinda Gates Foundation. Dr. Sayre received his doctorate degree from the University of Iowa and did postdoctoral work at Harvard University. Please join me in welcoming Dr. Sayre.
Good morning, and I'd first like to thank the organizers for the opportunity to speak here. I'd also like to express my gratitude to Jack and Andy Taylor of Enterprise Rent-A-Car, who had the vision to invest $25 million in the Enterprise Rent-A-Car Institute for Renewable Fuels. As you may know, Enterprise Rent-A-Car has the largest fleet of automobiles in the world at the present time, and they take it very seriously, the gas mileage of that fleet. And I'm proud to say that they have the highest gas mileage of any rental car fleet also in the U.S. Today what I'll be telling you about is a lot of science, but with a lead up to why we think microalgae have a great potential to provide renewable fuels in a carbon neutral or a carbon negative approach to meet our domestic energy demands. When I came to St. Louis 8 months ago, the price of gasoline, and if I can figure this out, and I'm not, yeah, well, the price of gasoline at that time was about $4 a gallon. We were all thinking about, what's the mileage that we're getting in our cars. There was a great demand for hybrid automobiles. But of course, since then, the price of gasoline has dropped substantially. But there are other issues that are still on the radar screen that are relevant to renewable fuel technologies. And one of those that's most important, of course, is the impact of a carbon-based fuel economy on the environment. And as the lower right-hand, right-hand slide indicates, as the CO2 emissions have increased over a time, there's a correlative increase in global warming. And we now recognize that that impact is substantial. There's policy that is emerging clearly to address the issue of carbon emissions, both from automobiles as well as from power plants. Another important driver, though, that's impacting our energy economy, of course, is security issues. Much of our energy, of course, is imported. That wasn't the case 50 years ago. But over 50% of our energy is now imported from parts of the world that generally have unstable governments. It's been estimated that we may be spending as much as $3 a gallon in Department of Defense commitments to secure the gasoline that we have. So that's a hidden cost that we don't actually see at the pump, but you see in your taxes. But the other more important issue is that many of our dollars are being shipped overseas to pay for fuel that is used in the U.S. And if we could keep those dollars in the U.S., that certainly would have an impact, a favorable impact on the economy. Well, we've heard over the years this term peak oil. You can also call it peak fuel. There's been a lot of controversy about this curve. It's a curve that shows the resources, fuels that are available in the world and their rate of consumption. And it's been estimated that either at the current time or maybe 25 years from now, we'll hit a decline where the rate of consumption will exceed the rate of production, and we'll recognize that we have a finite resource of extractive fuels available in the world. So we're facing a dilemma here of reduced fuel availability. But also, because much of our economy is based on carbon-based fuels, we're also facing the impact of global greenhouse gases on warming of the atmosphere. And as this slide indicates, there are a number of variables that can impact global climate. But it's quite clear simply by looking at this slide, looking at the slope of the curve for the greenhouse gases, that the contribution of greenhouse gases to global warming is the most significant of the factors that are indicated on this particular slide. So we're going to have to address this issue. It's been estimated that within a few years that the North Pole, the ice caps on the North Pole, may well be gone in the summer. And that will be a substantial impact not only on the wildlife that lives in that area, but also on our environment as sea levels rise, and on the weather patterns that we are familiar with now. Now, I'm proud to say that this is a map that shows states, and when I was driving up to Columbia this morning, I was listening to NPR, and they were saying that many of the cities are actually taking leadership roles in renewable energy. We just heard Governor Nixon put in place an executive order to reduce the energy usage in state buildings, but the states and the cities are often taking the leadership in legislating renewable energy and reducing our demands on foreign energy, and also reducing our impact on the environment as we consume that energy. And in the Midwest, as you see, Missouri has taken a leadership role in 2020. 10% or more of the energy in the state needs to be renewable energy. Now, unfortunately, there are other states in the Midwest that have not followed suit. And as I'll point out later on in the talk, it's some of these areas that have the best potential for renewable energy in the country. So renewable energy, as was pointed out by the governor, is also an opportunity for new jobs. And this slide is from the World Watch Institute. It indicates that several million new jobs have been generated in the last 10 to 15 years in the area of renewable energy technologies. And as you can see here, biomass, which is quite relevant as a renewable energy strategy in Missouri, outpaces the other technologies in job creation. Many farmers, of course, are involved in renewable energy technologies. The processing plants also generate jobs in biomass technology. So for the rest of the talk, I'll focus exclusively on biomass, and more particularly on algal biofuel systems as one of the most effective strategies for not only addressing domestic energy needs in a renewable way, but also reducing our carbon footprint on the earth. So as indicated in the slide, there are several advantages of renewable systems, most of which I've mentioned earlier, but there are also some constraints on biomass production. The amount of energy from the sun, which is fairly constant, at least at the outer atmosphere, but of course varies seasonally in different parts of the country, is very low. This is low density energy. We also have the issue that was mentioned earlier about biomass potentially competing with feed. Now, I prefer to use the term feed rather than food, as I learned recently at a biomass conference in Utah that 70% of the agriculture in the U.S. is solely dedicated to feeding cattle. And if we move to a chicken or a pork-based food system, that we would substantially reduce the acreage required to feed animals. And so the impact of biofuels on feed costs is an artificial impact in many senses. There are technological hurdles. I'll address some of those in a moment. With biofuels, where we're working with renewable crops, there's an opportunity for a variety of different crops for different parts of the country. So this is going to be a mixed fuel economy. And another constraint is the seasonality of the harvesting. Many of biofuel crops can be harvested only once a year. So if there's a failure in the system, if there's drought or disease or pestilence, there's a possibility that the harvest will be reduced for that particular year. So in an integrated biofuel technology, as shown on this particular slide, it would include biofuel dedicated crops being grown by farmers. It would include potentially harvesting residual biomass from the forest, and there's a great potential there, of course, in Missouri and other parts of the country to harvest fallen trees or diseased trees or small trees as a source of renewable energy. But also there are opportunities to recycle carbon, newspaper, cardboard, etc. in this biofuel or biomass generated economy. And so as you might imagine, there are lots of opportunities for employment in various aspects of this technology. Well, if we look at the impact of biofuels globally, it's clear that it's on the rise. I spent 3 months in Brazil on a Fulbright fellowship in 2007 at the University of Sao Paulo, and Brazil really was a leader in renewable fuel technology. Brazil currently does not import any energy. It's all generated domestically. The price of ethanol at the pump in Sao Paulo is half the price of gasoline, and the gasoline contains 25% ethanol. They have flex fuel cars in Brazil that can use any type of fuel or any mixture of fuels. So if one day you put in gas and the next day you put in ethanol, the engine self-adjusts so that you get the best mileage from the mixture. So Brazil's really taken a leadership role, and of course most of that is ethanol being produced by sugarcane. But just in the last year, the U.S. has surpassed Brazil in the production of ethanol. By and large, all of that coming from corn or corn-based ethanol. Biodiesel is also making a small contribution, and I'll make some arguments that we think that biodiesel or oil-based systems have some advantages over starch-based ethanol technologies. So if you look at a map of the United States and you're trying to identify where are the best places to grow biomass or biofuels, you might assume that it would be in an area that has the highest solar intensity. That's obviously the desert Southwest. It has about 4 times the solar radiation as New England does. So there's quite a range in solar intensity across the country. But of course the desert Southwest has a paucity of water available, and many of the soils are very poor for actually growing biofuels. If you look at the distribution of water in the United States, it's quite clear that the Midwest and the eastern part of the United States has a clear advantage. And all biofuel systems are going to require some amount of water to produce that biomass. So the Midwest is particularly well suited as a region for biomass production, harvesting, and the generation of fuels. And this slide really brings that message home a little more clearly. What it shows is the distribution of residual biomass across the country by county. And it's also again evident that the Midwest, including Missouri, is well situated in terms of excess biomass productivity and availability that can be used for the production of biofuels. So what I hope to tell you about in the next few minutes is why I think in particular that oil-based biofuel systems have some advantages, not always, but some advantages over starch-based ethanol strategies. And then I'll touch just briefly on the newer technologies engaging hemicellulosic and cellulosic ethanol production. But there's recently been some assessments of the relative productivity of oil-based crops and starch-based ethanol crops. And these life cycle analysis studies indicate that oil-based crop systems can produce more energy per unit area, they're less producing, and they generate lower amounts of greenhouse gases. And so if we're going to have a sustainable energy economy, we also have to be smart about the choices that we're going to make for the biofuel crop systems that we'll be working with. This slide summarizes the relative productivity of the major oil biofuel crops that are currently under consideration or in production. And if you go to the bottom, at the bottom is the category microalgae. And there are two scenarios listed there. One is a very optimistic scenario that's really pushing the theoretical maximum amount of productivity we might expect. And the lower number is what we really probably can achieve now. But the message that comes home from this is that microalgae, based on these numbers, have the potential to produce 10 to 30 times the fuel of any land-based crop system per unit area. This particular number has caught a lot of people's attention. The number was actually generated by a Department of Energy study that was conducted over 20 years at the National Renewable Energy Labs. And at NREL, they were able to demonstrate these kinds of numbers, the lower value, could be produced with very low technological inputs. So there is an empirical basis for these kinds of numbers. But the other important number that you see on the far right side of this column is the land area that's required for growing microalgae. So this figure shows in the larger yellow box the amount of corn that would need to be grown to produce ethanol to displace all of the gasoline in the United States. The smaller box is the actual crop area of corn that was grown in 2006. And so you see that corn by itself cannot meet our energy needs unless we were to substantially increase the acreage that was currently under production. The gray box on the right demonstrates the potential to produce alcohol or ethanol from cellulosic and hemicellulosic digestion. And what that involves is not only the starch that's produced by the corn plant, but also taking the stems and the stalks, the leaves, and digesting that cellulose and hemicellulosic material to produce sugars, and then fermenting those sugars to produce ethanol. Now, a variety of other hemicellulosic and cellulosic sources exist. We're hearing a lot about miscanthus, a very productive perennial crop that is being explored in the state of Illinois. Switchgrass, alders, there are a variety of sources of hemicellulosic and cellulosic sugars. But then on the far left is the area in the best case and worst case scenario for producing oils from algae. And the take-home message here is that the area is substantially less than it is for the cellulosic and starch-based ethanol strategies. So why are algae so wonderful? What is What is it unique about the algae that provides this potential to produce fuels? And it comes down to the fact that algae can accumulate up to 50 and sometimes 60% of their mass as oil. And these are actually droplets. Those are the yellow droplets that you see inside of this algal cell. And when we grow algae and harvest it, we harvest 100% of the biomass. That's not the case with corn, where clearly we're only harvesting the ear. Or if we're looking at cellulosic and hemicellulosic strategies, we may be harvesting only the top of the plant, but not the root. Very importantly, we can grow and harvest algae every day of the year. That is a particularly unique strategic advantage for algae, and it's for this reason that the Department of Defense is particularly interested in using algae as a renewable source, carbon neutral source of domestic energy production. And in fact, our laboratory is funded by the U.S. Air Force Scientific Office for Research. The Air Force recognizes that they need oil-based fuels. You can't fly a jet on ethanol. The energy density is half that of oil-based fuels. And the technologies don't exist for flying aircraft on hydrogen, though that's certainly under consideration. But for at least the next 50 years in our discussions with Boeing aircraft, it's clear that they need an oil-based system to produce fuels to fly aircraft. And so algae are, for that reason, very attractive to the Department of Energy. Another important feature, though, is that they grow very fast. They increase their size, the volume of biomass that's produced in a matter of hours rather than years. And due to the fact that they are grown in ponds, you can actually capture carbon dioxide from, say, a power plant, a coal-burning power plant, by bubbling into the pond. It'll stay in solution in pond and not go into the atmosphere as readily. And that bicarbonate, which is in the pond, then is available for the algae to grow. So this is a very busy slide which describes some of the challenges that we're facing with algal oil production systems. And it can be divided up into two groups. Actually producing the algae and getting the best yield. And there are a number of variables here that I won't dwell on at this moment. And then, very importantly, the bottom half is the harvesting. Harvesting accounts for half the cost of producing fuels from algae. And that's an area that needs a lot of engineering attention. When you think about it, it turns out that only 0.1% of what's in a pond is actually algae. 99.9% is water. We have to move a lot of water to harvest that algae, and that's hence the high costs associated with producing fuels from algae. So at the current time, it's not economically feasible. Even though the potential to produce fuel is much greater than other systems, the economics don't work. But in a number of companies, and some of which I'm associated with, in their life cycle analyses with the new technologies that are coming down the pike, we think we can get to $2 a gallon in the next 5 years. And hopefully that'll be a reality. Now, one of the questions I often get asked about growing algae is, can you grow it in the Midwest? We have harsh winters, and the expectation is the ponds will freeze and the algae will die. Well, it actually turns out the real issue is not the cold of the winter, it's the heat of the summer. And what this graph shows is, in blue is the ambient temperature, in red is the temperature of the pond, and in the green, between the green lines is where the algae want to be. And in the summer, which is on the right, you see the red line goes above the green lines, whereas in the winter the red line stays within the green lines. And so it actually takes energy to cool the ponds in the summer in the Midwest, and it doesn't take a great energy inputs to keep them warm in the winter. So growing algae in the Midwest is certainly feasible. So in our group we're trying to improve the productivity of algae, and we're using genetic modifications. I'll tell you about a few of those here. But algae offer unique opportunities for genetic modification. We can do things with algae that we can't do with higher plants. And one of those is that we can actually increase the amount of energy from the sun that can be used for photosynthesis. And we can do that by shifting the frequency of the light. We shift it from colors that are not absorbed by chlorophyll to colors that are absorbed by chlorophyll. So more photons are actually available for photosynthesis. And we can do this in ponds because we can put dyes in ponds that absorb green light and frequency shift it to red light, which is absorbed by chlorophyll. You can't do that in a terrestrial system. We can increase the efficiency of carbon dioxide fixation, and we can supplement algae with sugars to actually boost the oil production, similar to what you do with yeast when you make ethanol. So this figure just shows the distribution of energy from the solar spectrum, and the take-home message here at the bottom is that the chlorophyll absorption spectrum, which is shown in white there, has a big window in the green part of the solar spectrum. There's a lot of light in the green part of the solar spectrum that we're not using. We can't use for biomass. And one of the things we're trying to do is actually shift that light to red light so that we can use it for photosynthesis. Another problem with plants and algae as well is that they light saturate their photosynthesis at about 25% of full sunlight intensity. So 75% of the day, they're wasting 75% of the energy that's coming from the sun. They're dumping it off as heat. So what we'd like to do is make use of that energy that they're dumping off as heat, and one way to do that is to reduce the size of the number of chlorophylls that are found inside of the cell that are actually harvesting that light. That reduces the ability to absorb light, but it actually increases the efficiency of photosynthesis. And I'll skip through this slide fairly quickly, but it turns out in an experiment where we did this, where we reduced the size of the number of chlorophylls, or the number of chlorophylls in the algae, that the productivity, particularly in deep ponds, goes up substantially. In our analyses by a factor of at least 2. So we can engineer photosynthesis to make it more efficient in algae. And again, this is harder to do in terrestrial systems. But one area of interest that many companies are focusing on is actually using sugars to feed to algae to convert to oil. And as you can see here on the lower right, we get a 50-fold increase in oil productivity by feeding sugar to algae. They're very efficient at this conversion. And there's a company based in San Francisco that actually is building all of their technology on using sugars to make oils from algae. Now at the Danforth Center, what we're doing is we're engineering, we're using molecular biology to increase the efficiency of photosynthesis. And we're also focusing on transformative technologies to harvest oil from algae. And as I indicated earlier, that's a major part of the cost. So the current technology for harvesting algae is destructive. You actually kill the algae to get the oil out. And that's a great loss because you have to regrow all that algal biomass to make more oil. And so what ideally we'd like to have is a strategy where we don't slaughter the algae. We actually milk them, just like a cow. And then they go back to the pond and make some more oil, and they come back to the factory, and we milk them. Now, we won't do it with little tweezers, obviously. But what we have instead is a new technology which is being explored by a number of companies, in which we can use organic solvents called alkanes. These are actually the components of diesel fuel, and they will remove the oil from the algae without killing the algae. Now that sounds incredible. If you poured diesel all over you, you'd think you'd be dead. Certainly if you lit a match, you'd be in trouble. But with algae, it turns out these solvents can selectively remove the oil from the algae without killing the algae. And what we find is that we get a 3-fold increase in biomass productivity by milking algae rather than by slaughtering them. So, and a 40% increase in the oil that's actually recovered from these algae. And we can do it over and over again, just like the cow. You send it out in the field, it gets fat, it makes a little milk, you bring it back in, and you harvest that milk. And so this just shows that we can do it over and over again. So in our integrated system, what we have here now, and Many of the leading companies that are developing algal biofuel systems now have these more complex integrated systems approaches. We not only grow the algae, but we do this heterotrophic boost, as we call it, where we feed them sugars, they make more oil from the sugar, we milk the algae to get the sugar or the oil out, and then send them back to the pond. But down at the bottom, where it says methane, biomass, VHC, and charcoal, you see there's some co-products that are being produced. And it's those co-products that offset the costs and are going to help us get down from $35 a gallon to $2 a gallon. And again, in our life cycle analyses of these systems, we now think we can get to that level of cost within the next 5 years. So last of all, what we have here on this slide is sort of an idealized version of how algae are going to save the world and make us all rich as farmers in the Midwest. Thank you.